guys, welcome to the last lesson in chapter 4. Again, remember we're going to start reviewing Monday and Tuesday, and we will have our test on Wednesday most likely. So start planning for that, plan ahead. We are going to start up the second quarter with a major score, which will be that chapter 4 test. So you want to make sure you can put yourself in a good position for the rest of the quarter. Make sure you're prepared. This lesson today, 4-8, talking about patterns, it's a pretty light lesson in comparison to some of the things that we've talked before. Our goal is to recognize numerical and visual patterns and predict future outcomes. At the end of this, I'm going to show you something kind of interesting about how patterns come up into nature. All right. So first, let's talk about what we've mastered so far. So far, we know how to do things like this very fluently, right? We know how to determine whether this is arithmetic or geometric. All right. And this particular one here is arithmetic because I'm adding 2 each time, right? My common difference is always 2. So like if I find the next 3 patterns, that's going to be 9, 11, and 13, okay? And if I want to find the 15th term, we know that I would say a sub 15 is equal to a sub 1, which is 1, plus I have my n value, which is 15, minus 1, times my common difference of 2. Simplifying that down, I have 1 plus 14 times 2, sorry for the sloppy writing, is equal to 28 plus 1, which is 29. We know how to use this formula. We've used it before. So then I would say a sub 15 equals 29. We've also been able to do things like this, where our pattern is geometric. Okay, I know it's geometric because I'm multiplying by -3 each time to get to my next one. Notice we have negative, positive, negative, positive. I know that's going to be a negative R value then. And so I can do things like find the nth term. So we know that a sub 8 would then be equal to -2 times my R value, which is -3, and I put that in parentheses, to the 8 minus 1, which is 7. I say that's equal to 2 times my -3 to the 7th power. And I say that I have my -2 times -3 to the 7th power is, if it's an odd, so I end up with a negative answer, 2,187. Okay. And now I multiply those two things together and I get 4,374. So the 8th term of this, a sub 8, is equal to 4,374. And we've done problems like this. So this is what we've mastered so far. All right. So other ways to apply the ideas of patterns is to apply it to things that we see visually, right? So when we apply it to things we see visually, let's look at the pattern I have here. I have squares all the way around. And I know they're squares because I have a 1 by 1, I have a 2 by 2, a 4 by 4. So what would happen? How many squares are in the how many squares are in the 6th one of this, right? The 6th iteration of this pattern. Well, I wouldn't want to do that and count it all up. What I would want to use is work a little bit smarter, right? So in the first pattern, I have a 1 by 1. This one is a 2 by 2. This is a 4 by 4. Well, how am I going from one to the next? I'm obviously multiplying by 2. So the one after that is going to be an 8 by 8. So that's 1, 2, 3, 4. Then one after that is going to be a 16 by 16. And the one after that will be a 32 by 32. And all I have to do then is multiply 32 by 32 to get 1,024. And now I can answer that question. And I don't even have to draw the pictures. All right. So we can use our knowledge of patterns and apply it to visual aspects like this to come up with answers without actually drawing 1,000 pictures, or in this case, only 6. All right. Other simple ways to apply it. What if I wanted to find the next 2 iterations of this? Well, if you look, I have a circle, and then the next one comes through halfway, and I fill it in, and the next one comes through halfway. So I can do that again, come in halfway. And I know that's not twice as big, but I fill that in. And the next one gets just as big, okay? So another way that we can use, I know that these are not perfect circles. I know this probably looks like a crazy snowman or whatever, but we can use this idea in order to come up with patterns, right? And apply them to things that we see around us. The next thing that I can ask about this, I can ask a lot of questions. This is the triangle that you see in the how many triangles are there question. By the way, try to figure this out. Come back Monday and try to tell me what the answer is. Tell me what you think it is without looking it up. Challenge for you, okay? Anyhow, the next thing that I can ask you is, what does the next row look like? What does the next row look like, right? Well, I can say I have 1 and then 1, 2, 3, 1, 3, and then I have 1, 2, 3, 4, 5, right? And I have 1, 2, 3, 4, 5, 6, 7. Okay, so how am I increasing from one to the next? I'm counting by twos, right? So the next one would have 9, and the one after that would have 11. And I could use this, and I can go back and I can ask you, tell me how many triangles would be in the 29th row, and you would use your arithmetic series formula. Your arithmetic formula would look like a sub 29 is equal to 1, because that's your a sub 1 value, plus 29 minus 1 times the common difference of 2. And you can tell me what the 29th row would look like without actually drawing it out, because that would be kind of ridiculous. All right. Really, guys, that's the gist of what your lesson is going to be. It's short, sweet, to the point. But what I do want to end it with is a way that we can kind of think about patterns in nature. And I found kind of a cool video for you to watch. And so go ahead and watch it. Okay, here it is.
Math wasn't made up to harass English majors. It was invented by a little something called nature. And it's everywhere you look. In fact, there are specific numbers that we see in nature all the time. Together, they're called the Fibonacci sequence, and it goes something like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. You may know this pattern: the first and the second add up to the third, and the second and the third add up to the fourth, and the fourth and the fifth add up to the sixth, and so on. The sequence was first described by mathematicians in India about 1,300 years ago, and it was introduced to the West in 1202 by Leonardo of Pisa, aka Fibonacci, who is also responsible for introducing Arabic numerals to Europe, which, yeah, if he hadn't done that, we'd still be counting in Roman numerals, which would be terrible. Fibonacci was a mathematician, and in his book Liber Abaci, he described this sequence with the thought experiments about a family of incestuous bunnies. If you put one boy bunny and one girl bunny together, that's 2, and those 2 together will make a third, and those 3, when they're done, taking turns, will make 5, etc. The easiest place to find these numbers in nature isn't in bunnies, it's in plants. If you cut a banana into slices, you'll see that it has 3 distinct sections. An apple has 5. No matter what kind of flower you're looking at, chances are it has 3, 5, 8, 13, or 21 petals. Rows of seeds in sunflowers and pine cones always add up to Fibonacci numbers. Now, plants don't grow this way because they're receiving some kind of mysterious cosmic mandate. They're doing it because it's the most efficient way to pack as many seeds as possible into a small space. And if you want to see why that is, you can go watch Vihard's video, which is linked in the description, and it's awesome. But in addition to the numbers themselves, you also see the same ratio between Fibonacci numbers showing up. See, when you divide almost any Fibonacci number by the one before it in the sequence, especially the larger ones, you get the same number. 1.618, oh, lots of numbers. The Greeks discovered this long before Fibonacci, and they called it phi. Today, it's sometimes known as the golden ratio. Phi was purportedly used by the ancient Greek sculptor Phidias to illustrate the idea of physical perfection. He's said to have used phi as the ratio between a statue's total height, the distance from the bottom of its feet to its navel, for instance, and also the length of a face divided by its width. There's a whole other set of patterns in nature that are based on what's called the golden rectangle. A rectangle whose side lengths are successive Fibonacci numbers, like 8 by 13. This rectangle can be divided up into a series of squares whose lengths are also successive Fibonacci numbers, in this case 1 by 1, 2 by 2, 3 by 3, 5 by 5, and 8 by 8. When you draw an arc from one corner of each square to the other, they join to form a spiral that resembles many of the spirals we observe in nature. From the unfolding leaves of a desert succulent to the arrangement of those pine cone lobes and sunflower seeds and the shells of some snails. The math, you guys, it can be beautiful too. Thanks for watching this episode of SciShow. If you'd like to get in touch with us, leave suggestions or ideas, we'll be in the comments below or on Facebook or Twitter. And if you want to continue getting smarter with us, you can go to youtube.com/scishow and subscribe.
All right, guys, thanks for watching. Have a great weekend. We'll talk to you later.